Okay, so as I said, the first thing that we are going to do is recap of the basics of process control. Most of you, maybe except a handful of students, have done a first course in control. We are just going to recap some of those concepts. If you have not done the first courses in control, please go to NPTEL website and look at any introductory control course. So if you are a chemical engineer, an introductory process control course. If you are an aerospace engineer, an introductory aerospace AE control course. You can just view the lectures. Again, we are really interested in in the basics, just so that we have the same foundation to begin with. Okay. This is MPC does not use the same concepts that a traditional controller uses, because the traditional controller is the regulatory level, MPC is at the APC level. So not doing that course is not a big impediment, as long as you are ready to work those extra couple of hours this week in order to get yourself up to speed. Yeah, so we had talked about the basic control loop, and let us recap that. And this is for example a block diagram representation of a feedback control. Why it's feedback? Because we are measuring the output, okay, and we are using these measurements, comparing it with the set point, and that information is used to determine the manipulated variables or the manipulated inputs. Okay. Outputs would be controlled variables, inputs are manipulated variables, other type of inputs are disturbances. So we will call them as disturbances or disturbance variables. Okay. Let us take an example of riding a bike. Okay. You are riding a bicycle, you want to avoid potholes, you want to avoid obstacles, you want to avoid pedestrians. You might be going on an upslope, which means you will pedal a little bit more, you might be going on a downslope, which means you will pedal a little bit less. So that is the scenario that we are talking about. Okay. We will just talk about a few things with this particular example. So what do you think could be the control objectives? Someone, again, volunteers? Balance, so not to fall off, so being able to ride without falling off. One, what else? To stay in one lane. What else? To reach your final destination. Okay. So we will just stop at that. There could be multiple ones, and several others are valid. Not falling is kind of like the safety thing that we talked about. It's not a control action that is about reaching a set point or anything like that. It's about avoiding unsafe situation. So we could say not falling off as a constraint. Okay. So it can be an objective or it can be a constraint. Okay. If it is a constraint, that means you should absolutely not fall off. If it's an objective, then that means you should really not fall off, but if you really have to brake, it is okay to brake and then put your foot down and stand with your bicycle. So that would be the difference between not falling off as an objective versus not falling off as a constraint. Okay. The other, or probably the most important objective, would be to be able to reach a particular destination. Whether you should go in the same lane or not, that itself can be formulated either as an objective or as a constraint. Constraint means you have to keep in your lane, an objective means you have to keep in your lane as far as possible. If not, maybe veering out a little bit, you will get a penalty, but it is okay to do that. Okay, that is the difference between objective and constraint. What would be the control law? What you could think of as a control law? And again, there is no right answer or wrong answer to it. It's just various. Applying brakes. Handling the steering. Pedaling. Okay. I would say that all of these are manipulated variables. Okay. Because these are the things that you do change in order to meet your objectives. Okay. What would be the disturbances? Because we have formulated the control objective as reaching a particular location, there isn't exactly a set point. So it's an end goal tracking problem. It's not a set point tracking problem. Okay, it's a slightly different type of a problem, but that doesn't matter. I mean, we are really more concerned about definitions, and we have the same basic definitions. Disturbances. What could be disturbances? Closed off roads. Other vehicles. What about potholes? Right. Speed breakers. So basically various conditions on the road that you need to take into account when you are riding. Maybe when it rains, then puddles and all those also become disturbances. What are the measurements? Vision. Okay, let's break it down into a little bit more. So what all things would you measure with your eyes? Distance of a particular obstacle. What else?
Speed of a passing vehicle.
Speed of a passing vehicle or a pedestrian. Yes. What else? Pedaling speed. Yes. Angle of the road. Yes. Traffic lights. Okay.
Condition of the road in front of you.
Condition of the road in front of you. So, angle of the road, is that a manipulated variable? Let's say you're going on an upslope versus flat versus downslope. Is that a manipulated variable? What if you have two paths? One is a straight path, other is a path like this. In that case, would angle of the road be manipulated variable? It's more of a decision. How do you actually go to this path or that path? For example, with your steering, right? So the angle of the road would not be a manipulated variable because it's not something that you vary. You take path 1 versus path 2 based on whether you want an upslope, downslope and so on and so forth, but what you are actually changing is the steering. Again, I am taking a little bit of a fuzzy example over here, but again the idea over here is to get the concepts from this example. Okay. There could be auditory measurements as well. For example, someone from behind you is honking. Okay, so it doesn't only have to be eyes. It could be feel also, right? You are bicycling very hard and you feel the air rushing very fast. Yeah, oh, maybe I'm going too fast because you don't have a speedometer. Probably you can take your whatever Google devices out and you can check your speed, but not a good idea to do that. It's a good idea to keep focus on the road. Okay, so that would be example of riding a bike. Okay, let's move on to another example, more process example. Let's say we have a blending system. Okay, what we want to do is we want to get a certain concentration of A. You have a concentrated mixture of A and B, and you are diluting it by adding pure B. Okay, so you have a mixture, you have pure B, and you are getting another mixture out. Okay, and you are going to want to design a control system for that. So what are the inputs to the system? So mixture, the A plus B mixture, there are two inputs. One is F1, that is the flow rate, another is the concentration of A in that mixture. What else? Same with B also. So the flow rate of B. What else are inputs? Stirring speed. Okay, we will assume that it is a very well stirred system. That is an assumption that we typically make in chemical engineering, but yes, if it is a very viscous sort of a system, yes, stirring speed would also be a manipulated variable. What else? We will assume it to be isothermal, but yes, in a case where the temperatures are different, temperatures would also be inputs. F1, X1, F2. What else? Height of the fluid will affect, but is that an input? It is a consequence of changing the flow rates. So it is not an input. So maybe that is an output. What else? Yeah, volume and H are the same because volume is just H multiplied by A, but right, yes. What about FO, F out, is that an input or an output? So how many say input, how many say output? Input, show of hands, 1, 2, 3, 4, 5, 6, 7, not tentative, right? It is okay to be wrong. Proper show of hand. How many say output? Okay. Why do you say input? Somebody who raised their hand for input. How much is coming out is something that is in your hand to change. Why do you say output? Yes, composition is something that is determined by the overall process. What about FO? We'll assume that there are valves over here. I have just not shown. Let me do that. Good point, but yeah. Okay, let's put the valves there. Yeah, someone who said output of for FO. FO is also controlled by F1 and F2. So again, so let me just answer, it actually depends. For example, in most control systems, FO will also be an input. Why? Because you will have a valve that you will be able to change. Okay. In several control systems, it will not be an input if, for example, you do not have a valve that you can change. In that case, the height of the liquid column will determine what the FO is. Okay. So, FO can be an input or can be an output. Okay. Let us consider the case where FO is an input itself, okay, where you can possibly manipulate it, okay, and as he had said, XO is an output. Okay. This is especially important for chemical or mechanical engineers to understand. There is a difference between input to a control system and an inlet to an actual reactor. Okay. This is an outlet stream. Okay. Something about the outlet stream was an output from a control system, something else from the outlet stream was an input in the control system. Okay. Outlet is what comes out of that physical system. Output is the consequence of you making any decisions or the particular thing operating in a particular way. Input is something that you vary or something that gets varied environmentally. If you vary, it becomes manipulated. If it varies, arbitrarily for some other reason, it is not a manipulated, it is a disturbance. Okay. And this is, let me just finish it. This is a block diagram for that system. These are the manipulated inputs, this is disturbance, these are the outputs, constraints. Okay. So, for example, constraints would be this would be a constraint. Flow rate cannot be less than 0.
Capacity of the container.
Yes. So, let us say this was a 1 meter tank, these are constraints. Okay. This is an input constraint, this is an output constraint. Okay.
Composition of mixture A plus B is also an input constraint.
It is not an input constraint, it is in this case it is a disturbance. Why? Because you do not have, you usually what happens in a process system, you will get this liquor A plus B from a vendor, somebody else manufactures it, that gets sent to your manufacturing facility or your setup. Okay. There the specifications are always given as 2.5 plus or minus 0.1. So, it might be 2.4, 2.45, 2.5, 2.55, 2.6. Okay. things are never exactly at a particular value, they are in a particular range. Okay, that comes in from someone you usually do not have a whole lot of handle on it. So, therefore, it usually becomes a disturbance variable. Okay. F1 and F2 are usually something that you will change. Okay. As somebody mentioned, FO or F out could be something that you manipulate, or it is something that you do not manipulate. When do you not manipulate? If there is no, if there is just an on off valve over there. Okay. But if there is a valve that goes from 0% open to 100% open, it becomes a manipulated variable. So, again, whether it is a manipulated variable or not depends on the context, but most often what are inputs and what are outputs would really be clear from the context of the problem. Okay. So, that is the definitions that we are going to use of manipulated variables, controlled variables, disturbance variables. Okay. Of these controlled variables, sometimes both of them might be measured, sometimes only one might be measured. So, you could possibly have measurement of just the height and not of the composition, and then you would have to use an observer to figure out what that composition is, or sometimes you will have measurements of both height and compositions. You could even measure x1. If you measure x1, it becomes a measured disturbance. If you do not measure x1, it becomes an unmeasured disturbance. Okay. Why I am saying all of these? Because these are concepts that we are going to use when we start talking about MPC. Okay. So, inputs would be manipulated inputs, disturbances could be measured or unmeasured. Okay. Outputs would be controlled outputs, or and apart some of those or more of those controlled outputs would be measured as well. Okay. And finally, states. What are states is basically all the information that you need from the system in order to predict its behavior using a model. That is the definition of state. So, in this example, H and X forms the state, because you will have written a model of the form dH by dt equal to so and so and dx by dt equal to so and so. Okay. We will come to that in a bit. Okay. So, again, classification: in manipulated variables we will represent them as U, disturbance variables we represent them as D, controlled variables as Y, measured variables as Y. In the last couple of weeks of this course, we will distinguish between controlled and measured variables. That is when I will use YC and YM. For pretty much 10 weeks of this course, we will only use Y, because we will assume that all the measured variables are also controlled variables. Okay. And this is the definition of the state. These are variables that determine the internal dynamic conditions. So, as long as the state xk is known to you, the dynamical behavior of the system in the future you will be able to predict. That is the idea behind the state. And these types of systems are called Markovian systems, in the sense that the Markov property basically means that xk is sufficient for you in order to predict the future. You do not need xk minus 1, xk minus 2 and so on, in case you hear the term Markov in your research. If not, do not worry about that statement. Okay. Now, control configurations, most of you would have heard the term feedback. Feedback basically is compensatory actions. You measure the controlled variables and you determine the what the future manipulated variables are. Okay. So, based on that, let us say your set point was 2, your value is 1.8, you need to go towards that set point. Okay. So, that becomes a feedback, because you are measuring something and you are feeding back into the system in order to take the decisions. Feed forward would be anticipatory action. So, for example, if the disturbance x1 is measured, before the effect of the disturbance is felt on the system, you can take anticipatory control actions. That would be an example of a feed forward control. Okay. So, feed forward means you are anticipating the effect of something on your system and taking corrective measures before it affects the system. Feedback means you measure the effect on the system and thereafter take the corrective actions. Okay, again these are something that have been covered in your control course. Feed forward feedback basically means that it combines the elements of both feed forward and feedback control. And inferential is something that we talked about. Let us say you are interested in controlling the composition, but you are measuring only temperature and pressure, or you are only measuring the height. Okay, so you are inferring the concentration and then you are trying to control it. Okay, again inferential control, we will come to that in the week 10 or week 11 of this course. Okay, so pretty much for the most part of the course you do not have to really worry too much about it. Okay, MPC in general, we really usually don't talk about feedback and feed forward. It has components of both feedback and feed forward. Why does it have feedback? Because you measure the behavior, you do the estimation and you use the estimates in order to predict the future. Why does it have feed forward? Because it is a model based system. So if a disturbance variable is measured, you can predict its effect on the overall system and take corrective measures. Okay, so we usually do not talk about MPC in context of feedback and feed forward, but MPC could or would have components of both feedback and feed forward. Okay, let us take the example of the blending system. So what you can maybe do in the book, in your books or something is classify A, B, C, D whether they are feedback or feed forward. Okay, AC is controller. Okay, AT is transmitter. Transmitter basically means a measuring device which gives the information to a controller. Okay, maybe just spend a couple of minutes to figure this out and then we will discuss. A would be measuring the concentration. So you are measuring the concentration and based on that you are manipulating the valve. So A, is it feedback, feed forward or combined? Feed forward. Okay, because you are measuring the concentration of the inlet and taking actions, predictive actions before it affects the overall system. What about the second case? Feedback, yes, okay, because you are measuring the consequence of your control actions, you are measuring the consequences of everything after it has gone through the entire process. Okay, so this is feedback. What about the third case, case C? Feed forward, feedback, feed forward. Okay, it does not matter whether you are manipulating this guy or you are manipulating this guy. Okay, irrespective of that, you will see over here feed forward is this measurement affecting or being used to manipulate any of these. This would be feed forward. Okay, and the other one, if you are using any of this, this would be feedback. So therefore, having a block diagram representation often helps in understanding your control system. Okay, and what about this? Both. Okay, so this is the feed forward component, this is the feedback component. Okay, let us talk about transfer functions, seesaw transfer function. How does a transfer function, this is the first order plus time delay. Okay, typically this transfer function will the step response to this will look something like this. Okay, if tau is positive, we are going to have a stable system. So if the manipulated variable is changed like this, if you give step change to the input, this will be how your output looks like. This time delay is theta. Okay, thereafter there is a first order response. Okay, we have talked about poles, zeros and gain. K is the gain, okay, right. What is the pole of this system? Minus 1 by tau, okay, and because the pole is negative, therefore, the overall system is stable. Okay. Second order system. So, lot of times you would have studied a second order system like this, okay, where tau is the time constant, zeta is damping coefficient. So, what happens over here is, depending on the value of zeta, you will either get a behavior like this or you will get a behavior like this. Why do you not get a behavior where this keeps increasing or an unstable behavior? Okay, let us talk about a more general case. When will you get an unstable behavior? So, when will you get a behavior like this? Most of you said this just half a minute back. When the pole is on the right half plane, right, okay. Why? Because the right half plane, so if P1 and P2 are the poles, okay, you will have a component P1t and e to the power P2t. If P1 and P2 are both negative, then it is stable. If any one of them is positive, it is unstable, okay. If they are complex conjugate, it will be oscillatory. If they are complex conjugate with a negative real part, it is oscillatory but stable like this. Complex conjugate with a positive real part, oscillatory but unstable, okay. And then you have the 0. What if the 0 is negative? What do you get? Inverse response, okay. 0 is negative basically means that you will, let us say you will get a response of this nature where this is the inverse response, okay. What if the 0 lies between the two poles or before the first pole? Any idea? Overshoot? Not done? Don't remember or not done? Okay. Read that up quickly. I mean, not that it is really important, but it is always a very good idea to have a reasonable amount of comfort with these things, because these are going to come again and again and again, poles and zeros and so on. Okay. MIMO systems. Typically, when 90% of the UG courses, MIMO systems are not the only thing. The only thing I remember when I was a student or when I have taught, I have never taught a UG control course. I have only been a teaching assistant when I was a student. The only time we have looked about MIMO is how to get a decoupler and how to have multiple CISO loops. MIMO is much more than that, okay. MIMO is lot of times about the interaction between multiple channels, and we will talk about that when we talk about MPC, okay. With respect to MIMO, I will not assume any prior knowledge, okay. So, if you do not remember a whole lot about MIMO, not a problem, okay. And most important thing, MIMO is not M multiplied by N CISO, okay. We are not going to cover MIMO in that way. MIMO basically is a independent M by N system, and this is something that we had covered earlier. Just as a recap, I will quickly go over in 2 minutes. Hierarchy of control, advanced process control or MPC is going to sit in this particular layer. Regulatory control, these are your PI loops, PID loops, okay. Advanced process control, for example, you want to maintain various values at the set point. You want the distillate at its set point, you want the bottoms at a set point, you want to minimize the amount of energy that goes into this heating. All of these 3 things you want to handle, and you want to handle this in a MIMO sense. There are 4 controlled variables, 4 manipulated variables, everything is in the MIMO sense. How do you do the control? That is what we are going to talk about in this course. In the next 12 weeks, that is what we are going to talk about. Scheduling and planning is even higher level, and this is basically daily to monthly basis based on the feedstock, based on the overall demands. How do you determine the interaction, the various flows operation of this overall system.